Hi there, everyone. This will be a short relative to the length of the PowerPoint, but short review of the terms that introduce what an equilibrium system is. So we'll get right into it. By the end of this, we'd like to know what a chemical equilibrium is, identify different types of physical equilibria, which is just the plural form of equilibrium, read, draw, and interpret concentration versus time graphs. And then we'll use an ICE table to determine changes in concentrations mathematically, and then finally identify real-world scenarios where this actually occurs. And we'll do that throughout versus a specific slide. So you learn early on that they're in a reaction. The arrow represents the products, the reactants being turned into products. And we call that completion when we see the one-way arrow. But sometimes reactions stop before that, and some of the reactants are left over once all of the products have formed. And it looks like an incomplete reaction, but in some cases it's not. So if you look in the images at the bottom, right, you've got the first molecule and the second molecules reacting, and you can see that there's a mixture of them, and more of the black dots form over time. And what happens is some of the reactants, which are these red molecules, they represent water, are left over, right? So you're not seeing a full conversion. So we're going to look specifically at those examples. So we'll look at this in a little bit more detail here. What you're looking at is the conversion of nitrogen dioxide to dinitrogen tetroxide. So the reactants have a brownish color, you can see by the color of the vial over here, and the products have a yellowy color, and they're gases. So what happens is, once the product forms, which is N2O4, now if I just circle it, you'll notice that there are some of the reactants left over. No matter how long we let that go for, we could leave it for days or years. So what happens is there's a pressure within that environment that won't let those reactants turn into products. It's not that it's an incomplete reaction, it's that some of the products are unstable and actually become reactants themselves, so they react in the reverse direction. This is what an equilibrium is, when you have products and reactants at the end of a complete reaction. So it's different than an incomplete reaction. It's the fact that some products actually form reactants. And you might be thinking, well, how will we know when that's the case? You'll look for that arrow right there, that double-headed arrow. Okay, so you'll notice that it's only half of an arrow on each side, right? That indicates it doesn't go fully to completion, but the products are actively turning back into the reactants and vice versa. So that's what an equilibrium is, and you'll identify it by that arrow at this point. So here's the definitions of it and the conditions of what an equilibrium is. All right, so it's a point in the reaction where all reactants and products have reached constant concentrations. That means they no longer change. Okay, so we'll have a little bit of each one left over. This is important that it's a closed system. If it's an open system where matter can escape, then there will be different pressures and an equilibrium won't be established. So the concentrations will always continue to change. We see it when there's a double-headed arrow, like you can see there in the bullet point. And at the end of the reaction, like we've said a couple times already, you'll see both reactants and products. So here's a graph just showing the concentration over time, and you can see that it levels off. And the point where the reaction levels off, right, is where the concentration line is horizontal. It's not changing anymore, right? So if we did the change in concentration, the slope would be 0. So like we had said with rates, reactants decrease their concentration and products increase. So if we write a reaction for this, it would be carbon monoxide plus water produces hydrogen gas and carbon dioxide, and that's balanced as is. Now because it is an equilibrium reaction, we'll change that single-headed arrow to a double-headed arrow, and that just means that it can go in both directions. So now we're going to look at this term called dynamic equilibrium. It's not enough that the reaction the concentration stays as they are. There's actually a little more going on there than it seems. So a dynamic equilibrium is going to be described as the rate of the forward reaction and the reverse reaction are equal. So for every reactant that turns into a product turns back into a reactant at the same time. there's no observable change, meaning that if you look at the system, you can't tell that anything's happening, but on the atomic level, there is. So we can make a note here. There is microscopic change, which we can't see. Okay, so as far as we know, the system is not doing anything, but on a smaller level, it is. And then finally, the reaction occurs in a closed system, like we said, so that matter cannot be lost, but energy can be exchanged. So if a dynamic equilibrium is where the rates of the reaction are completely balanced forwards and backwards, are two children on a teeter-totter an example of this? So just draw a teeter-totter here. We've got two children sitting on it, but they're not moving, they're perfectly balanced. Pause and think about it. And if you've had a chance, your answer should be, it is not. Because dynamic equilibrium, I'm just going to short form that there. Dynamic equilibrium involves equal and opposite changes. All right. So in this case, no, this wouldn't be described like this, and we would describe this as a static equilibrium, where there's a balance. Equilibrium, check our spelling, right, where the forces cancel each other out, but there's no change at all. There's no microscopic change. All right, so for there to be dynamic equilibrium, there needs to be offsetting changes. All right, so what we're going to look at chemically for this is a couple of different processes. We'll look at solubility, phase changes, reactions, and acid and base. This will occur throughout the entire unit, so we won't see all of these today, but it's an overview. So to start with physical equilibrium, right? This is really what your phase changes are. Okay, and there's some examples there. It's wherever there's no chemical process, so it's a physical change, just as the name implies. It's still in a closed system, but in this case, there's no macroscopic change at equilibrium, so you can't see anything, right? And that's an important factor, but there's something happening. So the best example of this is if you were to place water at 0 degrees. Sorry, an ice cube rather than water. If the ice cube is placed in a cup of water, so we've got that, and this is what happens in the winter a lot of times too, where we get that freezing rain and the ice conditions on the road. All right, because it's at 0 degrees, that's both the melting and the freezing point. So for every particle of ice that melts into water, because it's at 0, a particle of water is going to freeze into the ice cube. So there's no net change in the amount of each. This is a dynamic equilibrium. We can't see the change happening, but we can measure it, and it's there if we wanted to. So that describes a phase change when a substance is at its melting or boiling point, for example. Now we'll look at when something's dissolving. So when a solute is placed into a solvent, what happens is we consider the solute a salt, right? It's a solid that splits up into its ions. At a certain point, it becomes an equilibrium, though. So the solute, which is at the bottom, dissolves particle by particle within the water, for example, right? And at this case, it'd be considered unsaturated because some of it is dissolving. So the rate of dissolving is greater than the rate of crystallization. So it's not an equilibrium because dissolving is the forward reaction, whereas crystallization is the reverse reaction here. Right? So in scenario 2, if we call this B, we call this A, B, and C, you can still see that it's still dissolving, right? We see there's 2 arrows, 1, 2 for dissolving, but now it's starting to slow down. It's approaching saturation, and one of the solute particles is recrystallizing. So the ions are turning back into the salt. And then finally, at the saturation point, we have a dynamic equilibrium. For every particle that dissolves, one undissolves or crystallizes. Right? And you can see it's equal. We lose one, and then we gain one back. So dynamic equilibrium is all about balance. Up until that point, it's not an equilibrium reaction, right? It's just a reaction proceeding, but it's important to recognize that the reverse reactions can occur as well. So we've summarized this. There's two types of reactions, one-way and double arrow. We'll know when to apply those. If we see one-way, it means it's a regular stoichiometric reaction, goes to completion, right? Fully changed to products. We have 100% completion. The double arrow means less than 100. And it varies based on what the reaction is. So there's no way of telling without more data. So if we look at these two reactions here, we call this a complete reaction, and feel free to try these by yourself. And we call this an equilibrium reaction. Sometimes complete will be referred to as one way. All right, so it's based on the arrow that tells us what to do. For here, we can use stoichiometry. Here we cannot. We need a new technique of determining the amounts and concentrations of products. So to be able to read this graph that we saw earlier, right, a couple of points: the reactant concentrations decrease and the products form. Now the new point is that once the change levels off and the graph goes horizontal, it reaches equilibrium. And you can see that's signified by the change in color here. Right. So now, depending on how much of the products form affects the ratio of what's there, products to reactants. So we'll classify the equilibrium reactions in a couple of different ways. We'll call this A and B. A left-hand equilibrium reaction, the concentration of the reactants are larger than the products, right? And that means it's not favorable and very little product is formed, but it's complete. Right? So if we were to compare that, for example, 75% are the reactants, and only 25% are the products. And you can see that the size of the arrows changed as well. Right hand, on the other hand, ironically enough, would be like the opposite. More of the products form than the reactants. Okay, and there's a smaller arrow indicating it went backwards there. So just some classifications that you'll notice as we go through. So if we write what the Haber-Bosch process is, right, and this is, I can't remember it, it's been a while, and it's the formation of ammonia, which is used in fertilizers, right? And we're told that it lies to the far right, which means that most of the reaction converts to products. If we do a concentration versus time graph, right, we're not specifying what the time is. We start with some amount of reactants, which decrease over time, right? And because it lies far to the right, they approach zero. But it's important to note that in equilibrium, the concentrations never touch zero, or else it'd be a one-way reaction. The products always start at zero because there's nothing there when the reaction begins, and they slowly increase and level off, right? And we're just sketching, so we're not attaching numbers. Then we would add a dotted line here to show that when they level off, equilibrium is reached. But as long as they're changing, there is no equilibrium. It's a reaction in one direction overall. Okay, so we're going to stop it at that point, and we'll do a part 2 to the video to look at the mathematics behind it. All right, and that part A was just the theory involved.